We're all okay? Alrighty, so sorry we lost an extra 5 minutes there, but despite having lost some time here due to stupidity, I can warn you that today, if I can get through all of it, today is the hardest lecture we will have. For certain. But then we'll get through it. The hardest homework set you will have will be the next one, because I remember I was warning you about it. And anyway, so I pushed off. There's one question it's pretty hard. You're going to do it with Mathematica, so maybe it's not that bad. But okay, so let's recall we're doing time evolution, and it's a unitary operator. Its job is to take the initial time, which will become 0 as we move forward. Just like I was really careful with my spin notation, SZ comma plus SZ comma minus. Eventually I'll shorthand it once you get used to this. And very similar to translation, it looks like this. And H bar makes the units work. We think that the Hamiltonian is the hidden operator inside of time evolution based on similarity with Poisson brackets, classical Poisson brackets. There's a little bit more to it. You can actually figure this out. You can actually reverse engineer this from the time, the time-dependent version of the Schrodinger equation. You can show that this is consistent with that. I won't worry about that, though. You may recall we had the time-dependent Schrodinger equation at the beginning of class, and I showed you how you separate it into 2 mini Schrodinger equations. The one we've been working with the whole time, and the time-dependent one, which we're getting into more today and the rest of next week. Okay, so there was this, and it acted on a ket, which, sorry, where am I at? Again, just to make sure that you're okay with how we write this. Okay, so alpha at time 0, this is what we've been dealing with. I never bothered to put it in time 0, it's usually 0, so I really shouldn't put in anything, but it will evolve to a later time. So that's the notation. Now this thing translates you dt ahead of time. And we had something similar, maybe don't write this down, but you may recall we had something similar with the translation operator that moved you slightly ahead of time. Dx. What did I just say? The translation operator, which is, the hidden operator was momentum, moves you a very small amount of space. And what we did was to move it a macroscopic space, to move it something that's actually finite. What we did was we took this thing, we raised it to the nth power as n goes to infinity. There's a little bit more trickiness to it, but it's a fairly simple ID. If you simply took this and over and over and over again, you're going to find that it's this. It's like delta x over n in the summation. No, anyway. So yeah, there you go. Yeah, I'm pretty sure that's right. Okay, so that's what we did with translation operator. The problem is, so let's say, all right, so we want this. We want to go from time 0 not to an infinitely short amount of time later. We want to go to a natural time unit, which is still a pretty small amount of time, but technically dt is an infinitely small amount of time. So today's goal is to do this. Now, last time, again, we raised this to the nth operator. So what you do is you bring this, you have this repeated n times. Dx would be delta x over n. You'd multiply it all out. You'd find you'd have a Taylor series for this. Again, it's a standard. There's nothing to it. But that is not going to work here. Okay, we're not going to raise this is the nth power Now, here's the reason why. It's because the Hamiltonian can be time dependent. That is the killer. Now, for the most part, we're not going to work with a time-dependent Hamiltonian, in which case, heads up, this trick that we did here, the limit is as n goes to infinity, that we did for translation, will actually work for time evolution too. I actually can do this. But in the case the Hamiltonian actually is dependent on time, then I can't. So I'm going to do it that way, the time-dependent Hamiltonian, and then I will shorten it down. I'll factor all the Hamiltonians out because they're all the same because they don't involve in time. And then we're going to get e to the minus I Hamiltonian delta t over h bar. That's what we're going to get. Okay, so I can and can't apply this. All right. Anyway, now when I do this, when I'll figure it out the other way, we're going to run into the hardest equation in quantum mechanics, pretty much. So heads up. Okay, the last thing, you know what I realized? I realized that I was looking at this trying to compare like how this looks like that, this is how we treated this, but we're not going to do that with that. And I just said all that. And I realized that maybe this looks like, well, we didn't actually use it. You know, I think if I just kind of looked at it. Notice its job is to take a wave function, wave function, and let's make it down so it's like a Gaussian. And what it would do is it would just move it to the right, like delta x, right? And I thought it was kind of neat. You're actually going to do something. I actually will have you do some like MATLAB to work on this, so you really understand how to deal with it. I think this is just way too abstract, right? Because let's see, what would you do? You would operate on a so you would operate on a state, right? But wave functions are usually, to make it a wave function as position. Notice I just drew it this way. I need to put it in the positional representation. I guess I need to put little primes on there so it's place keeping. So I realized this is kind of hideous actually. And I realized that. So I'll show you what to do here. What you do is you would expand the operator, right? So that would be 1 minus I over h bar delta x. Delta x is a number. Then way I'd have minus so that's 1 minus x squared. So that would still be minus, right? Because I'd have I squared. Minus is plus, but then I got an I squared that's minus. And I would have x cubed. Okay, so there's, it goes on and on and on. Okay, and I realize the reason this works, again, I want to point this out because we're going to get into some computations. When we get done with this, I'm going to show you how to do all this on MATLAB. I realize the reason this works, as much as this is kind of a bloody mess, is, of course, these are derivatives. And, so I realize what's happening is, and again, if we do this with MATLAB, what you're doing is, at any given point, you're going to start at the beginning. And then what you do is you look at the slope of the wave function, and you move along by the slope, right? So you see what I'm doing here? I am looking at each point, and I'm looking at so I'm taking each point, and I'm figuring out the slope, and I'm sliding along the slope. And that's why, that's it ultimately, I didn't really draw it well, but ultimately it moves it over. So anyway, I screwed that up pretty badly, really. Right, it would, anyway, it would do like this. So you're going to figure out how to do that in MATLAB. Now, of course, it has higher derivatives because a wave function, if a wave function was a line, you can stop right here. You can stop right here because a line doesn't have a double derivative, but a Gaussian, unfortunately, you can see why, unfortunately, you have to make approximations because a Gaussian, you see what a Gaussian would do, right? How many derivatives of a Gaussian, you know, e to the minus x, how many derivatives can you take before you finally hit 0? Right, a line, how many derivatives can you take before you hit 0? Okay, how many derivatives of x are there? Just one, right? What happens when you take the second derivative of a wave function that's just x? 0. And then the third derivative? 0. Okay. What about e to the minus x squared? Yeah, it goes on forever. So anyway, so you have to make some approximations with this. So anyway, this is coming up right after all this is over. So anyway, I just want to make sure that you looked at this and you didn't see something, you know, hideously abstract because then the stuff is pointless. Okay, so now back to task. Oh my God, what is wrong? Isn't this weird? Why is this happening? Okay, now again, this is going to be awful. Okay, no doubt. And I know I say that too much, but there's really no good way to say this. Okay, so here's how you start, and I'm going to have to go across the board, across the board, across the board, about twice, 3 times. Maybe -5. All right, anyway. So again, what I want. Now I'm going to write something kind of crazy that is ill-defined. So this is at time 0, and this is a later time plus a little bit more. Now again, I can't do this. I can only go from t0 to t0 plus dt. So I'm writing some stuff down that it's like, well, what is that? I don't know what it is. And I don't know what this is. Sorry, let me. There we go. Sorry, okay. All right, sorry. So I misspoke. I do know what this is, right? So again, I'm looking for this. So this, when you write this down, understand what the pieces are. This is what we're looking for. This you know, and this is also, I don't know. Now, the reason is again, I want to go from 0 seconds to 1 second. I can go from 0 seconds to 0 seconds plus an infinitely small amount. That's what this does. This is going from 1 second to 1 second plus an infinitely small amount. So this is actually our normal operator. It's just not starting at t0, which, why would that matter, right? Okay, so this I know. This I happen to know. And this, again, is kind of doubly screwed over because this is going from time 0 to a wave feature time plus a little bit more. So I don't really know what that is. So I will write this down again because, again, I don't know what it is. So notice that this is pretty crazy because I want to write a psi. And that sucks because obviously the board is not erasing very well today. I wonder if it's the humidity. Okay, notice that this makes sense because this is going to t. I don't know what this is yet, but it's going from t, and this is going from t to t, again, a small amount of time in the future. So, trick is that multiply this out. Now I'm going to do a little bit of algebra. It shouldn't be too hard for you to figure this out from your notes. I'm so sorry, guys. Just out of it. It didn't. swear I'm in good shape. It's that shape I've been in my life. But I'm still gonna ease and weave when I run. And I should be putting little hats on things. Okay. So I have this. So what I'm slowly but surely developing is a differential equation for this. That's what I'm trying to get to. And hats, okay. Looks like I'm committed to the hats. I was going to just drop the hats, but it looks like I started bringing hats. Okay, you folks in the back, I'm always terrified you're not seeing. Can you see this? I want to point out that this is the partial of the operator from. Okay, do you see that in the back? Okay, good. And I'll move over. But anyway, okay, look what I got. Here's the function. I don't know what it is, but this is the function, a minuscule bit of, it's moved over just a little bit. So function at t0t, t0t, but it's been smudged over just a tiny bit. So this difference is infinitely small. This is an infinitely small change. Okay, now I'm kind of thinking about, well, now what? Okay. Partials either need to be integrated. So now I can integrate this to find it, and I integrate this with respect to time. But I got something of a problem that's also, I don't know what that is. So if I'm going to integrate this with respect to time, and there's time right there, I got a problem because I don't even know what this is. Okay, now I can either integrate a partial, or what I could do is bring dt over here, and now I've got a derivative. Partials either have to be integrated, or they have to turn into derivatives, or they're meaningless. Or not meaningless, just zero. Right? Technically, this difference is infinitely small. Okay, so now what? So that's what I'm going to do. I'm going to bring this over, and now I'm going to have to start to change with respect to time. Now, you might want to just hold off writing for a second. Sorry. Sorry, I was a little bit clumsy here. Okay, so what I'm going to do is I'm bringing dt over. Tell you what, I'm just going to throw this. I'm just going to throw that out there. Okay, now the trick is, and this is going to be kind of painful. Now you recall that time, it was actually more important than I let on, about how I said there's no such thing as indefinite integrals. They're all definite integrals with tricky ways that you manipulate the limits, right? So watch this. I'm going to integrate this thing. I'm going to integrate this derivative. And I'm going to go from t0 to t. Okay. Now we got to be really careful about this, because now that my upper limit is t, this future target, it can't be here, right? No. So I'm going to have to make that a little dash, right? Now I keep talking about how we have placeholders, and they don't mean anything. Now if I'm integrating it, and here's the other part. This dash t. Okay. All I did was I turned these t's into dash t's because my upper limit is now the actual target t. Again, it was the same trick I used before to show you how there's no such thing as an indefinite integral. If I'm trying to just integrate with respect to t in an indefinite manner, really I'm integrating t dash with an upper limit of t. So anyway, I hope you remember that. And if anything, remember that these dashes are all just placeholders, but you can see how really hideously important they are. Okay, so let's see what this is. We'll worry about the other side in a minute. Okay, so this will be u of t naught minus the operator at t naught. Okay. Here. Okay, does this make sense? Upper limit, t naught minus lower limit, t naught. Okay, and this other side is, I'll just write it down to be careful. And I forgot the little cats. Cats, girl. Okay. Now, I see the number 1. Who sees the number 1? Huh?
The t0 t0.
Yeah. Remember, that's the time evolution not doing anything, which means, no, it can't be. It's either 0 or 1, right? And how did you know it's not 0? Because when applied to a cat, for it to translate it not in time, it destroys it, and that's nonsense. Okay, so this is 1. 1.0. Okay, now what you got is, now I'm going to do some manipulation. So notice that now I've got my target on the left, and I'm going to bring that other thing over, -1, so it's kind of nice to put it over onto the other side. Over H bar. You know what? I'm so sorry. You can't integrate one side without integrating the other. Sorry about that. Right? You see why? Now, the reason I forgot about that is because I didn't actually do anything with it. And again, all the t's become t dash, and the trick is that the upper limit is just our regular t, which can be 1 atomic second, 1 actual second, 1 year. It can be whatever it needs to be. Okay, so let's see what we got here. Okay. So the operator over an actual amount of time is 1 minus. Okay. This is where it goes donko nutso. I got no good way to deal with this, but this is what you do. This is not, what I'm looking for is t naught to t naught plus dt. And that's our regular operator. And then I can stop. This ain't it. This is t naught to some future time. Probably, yeah. I guess it'd be between t naught and t. Right. So I guess I've shaved down time. Right. So it's somewhere in between my limits. So I've shaved down the time. I've got t dash is now closer to t naught, but I don't know that it's dt to t naught. In fact, that kind of is impossible. So again, I kind of have the same thing here and here. Now again, 0 to 5 years. What the hell is that? And I've got an expression here that's basically the same damn thing. I kind of haven't really, I kind of worked in circles. I've worked in circles. It's just kind of nicer because this t dash would not be as long as 5 years. It would be something shorter. So here's the trick. And again, this is, this is going to want to make you kind of throw up. But here's what you do. You're going to insert this expression into itself. And here's what that looks like. Okay. Okay, now I am already looking at this thinking, I don't know if I have the room. See how careful I'm being? Okay. 1 minus that. Okay, so you've seen me write the same thing. And now let me stipulate that h, of course, is a function of t. Remember I was telling you that I don't actually have to do any of this if the Hamiltonian is not time dependent. Now, time dependent Hamiltonian would be like, imagine an electromagnetic wave, light. Light is interacting with the system, and light varies in time. Okay, so there's all kinds of time dependent Hamiltonians, and there's plenty that are not. A non-time dependent Hamiltonian would be like a static magnetic field, like our electrons going through a Stern-Gerlach. The magnetic field doesn't change in time, unless you were to take the Stern-Gerlach machine and like spin it completely. That'd be cool, but maybe we won't do that. Okay. So I should have probably put that little parenthesis in before. Okay, now, again, here's where it gets darko nutso. Notice that I'm writing this 1 minus I over h bar integral. I'm writing it again. 1 minus I h bar, 1 minus I over h bar integral. And in here, it will go to t. T naught will always be on the bottom. T prime will be the top deal. And we're going to have to integrate it. It will have a different, dash, a different placekeeper. So that'll be double dash. Okay. So let's see here. 1 minus I over h bar didn't change, integral t naught to t didn't change, h, I just made sure that you knew it was a function of t, because I'm integrating of t dash, because I'm integrating with respect to t dash. But then u ends up being 1 minus I over h bar integral. It needs to go to t dash, right? So you see why my upper limits are the same? T dash, okay, but then of course I have to, as a placekeeper, I can't integrate. You can't integrate to your upper limit, that's nonsense. It can't be the same thing. So placekeeper now I have double dash. Okay, now what do is, now notice t double dash is in between t0 and t dash. T dash is in between t0 and t. So you see how you're kind of shaving away the difference till you want to do this over and over again till t dash to the infinite power is then fairly different than t naught, and then you're done. So I'm going to have to write this for the next 5 years. So anyway, guess what the next step is? Do it again. When does it end? Never. Here, I'm going to stop here, and if you don't mind, I literally need a lot. I'm just going to simplify that. Now again, in your mind, just keep doing that over and over again, but I'm going to stop there and just do some simplification. And again, I need the room. I told you today was unpleasant. And it's unpleasant in terms of equations going out, out of this world. Being really freaking long. Okay, 1 minus. And that's why I need the bigger room. So I'm factoring. I'm doing some factoring at this point. I've got a lot of stuff here, right? So I can do some factoring. You may notice that there's an I over h bar squared here to here. I have to admit, I'm not. At this point, I'm not going to really point out what's connected to what because I'm not even sure myself. And now we're going to form a little nested. It was a little bit nicer to do it this way. And what the heck? Anyway, it looks a little bit nicer. And I keep writing side for u. this one more time. Now again, what you can imagine is that and then if I do the same trick again, that there's a third integral and a fourth integral. And the way you would deal with this, right, is you would make this evaluation, feed the results into, you do this integral, and it's still here, so then it gets integrated with respect to that. And again, there's an infinite number of these, so hopefully you kind of see how it's a bit of a Russian doll. Petrushka, is that right? Petrushka doll. Anyway, okay, so now let me write this out, assuming that I have done an infinite number. So now I can write it as a sum, and there's a little bit of a pattern recognition, right? Okay, so it turns out, okay, 1 minus I over h bar to the first power. The squared makes the minus sign go away. Technically, it's still minus because the I is squared. Anyway, so here, this is okay. That's clearly cool. Okay, then I've got the same deal. Okay, so now here is where it's a little different. I'm doing this t to the n times. Okay, so that's what it looks like. That's what it looks like. Okay, so this is it. This is time-dependent quantum mechanics. This is how you So notice that I've gotten. If you do it an infinite number of times, now I actually have a little confused. It does seem that this went away. I better double check my notes. This is gone now. So what you do is you keep integrating the Hamiltonian over and over and over again. Anyway, you see it in front of you. It's so complicated, to be blunt, even I'm actually pretty confused now what the heck I'm looking at. Well, so it's a sum, so it's a sum, right? And every member of the sum is a nested integral, where the first sum is too bad, it's just one integral plus double integral plus triple integral plus quartic integral plus whatever comes next. So, and then in the big picture, I also want to point out that you could never imagine anything more complicated than this. This is the ultimate in complication. I think I've seen someone use it once. This is so complicated, no one ever uses it. Seriously, it's too hard. Oh, is the camera still on? Okay, good. Okay. So I just wanted you to see this. There's nothing much more to say about it. You'll never actually use it because I wouldn't even know how to begin to be blunt. I mean, I think I could probably figure it out, but I'd rather not. Okay. Now notice I kept writing the Hamiltonian is a function of time. If the Hamiltonian is not a function of time, then what happens is U of t naught. This, by the way, just following how the book does this. Now, I can tell you this is that I think physicists deal with this a lot. So what I've done here is I've factored the Hamiltonian operator and I've raised it to the nth power. So I've just factored it all the way out. Now, so this would be like p squared, right? So p squared, t to the fourth, p to the 2, 4, 8, 16. Anyway, so h. You can deal with the power of an operator, right? It's unpleasant, but it's doable in your toolkit. Now, what you get left with is also a rather complicated looking thing. But as you can imagine, it's a whole bunch, it's a mess of integrals, right? But you're not integrating anything. You're just integrating partials. So, oh God, guys, can you see this? Because I'm truly, unfortunately, I'm stuck at this point. Is this better? Oh God, I'm sorry about this. Again, I cannot plan well enough ahead. I cannot plan well enough ahead for this. Okay, so that mess of integrals, that nested group of integrals turns into t minus t naught to the n over n factorial. And as a result, now I have to go over here because now I'm truly out of room. You can see why the lecture centers are awesome because they just keep rolling up the blackboard. That is really disturbing. I've never seen teams not come off like this before. You wonder, okay, what this turns into now is that because I'm not writing H and T. And this ends up being E to D. All that over H bar. This is the time evolution operator. That's it. Again, I could have just raised e to the minus h dt over h bar. I could have raised that to the nth power. The limit is equal to infinity. Now we've gotten the same thing, but I swear, I have seen this expressed sometimes, and where I've also seen this, I doubt you'll ever will, but when physicists talk about like Stephen Hawking stuff like black holes and quarks appearing out of nowhere in Feynman diagrams, that's where you see this thing, right? So you see this expression. If you ever see anything like this, you're expressing the time evolution of an unbelievably complicated something like quarks or black holes, stuff that in chemistry you're never going to see. This is our time-independent Hamiltonian, and most Hamiltonians are actually time-independent. So this is actually relatively easy. Where you don't have a time-independent Hamiltonian is like with light. With light, you can approximate light as a cosine, electric field times cosine, and guess what? If you have an electron, which is basically what we're always dealing with, then it's going to mess with the electron, right? And you're actually going to do simulations of this. Now here's the trick. If you make your delta t here, again, this isn't little d, it's big D, right? If you make this time step really freaking small, you can use this anyway. So if the Hamiltonian is time dependent, we still, we just use this anyway, right? Because screw that. No, I'm not doing it. Screw that. This is what you do anyway. And it's an error because this was solved with the time-independent Hamiltonian, yet the Hamiltonian will be time-dependent. And again, you're going to actually do simulations of this. And the trick is to make this as small as possible so this error from not using this expression, which again, I'm not even sure how to begin, the error from that is minimized by making your t and t naught as close as possible. Again, like 100th of a atomic time unit. So it's something like that. That's basically how you're going to do it. Okay, real quick, let me point out that Now what you want to do is calculate properties. You want to calculate the properties of the state. Now, so I can evolve the state in time now, and I would like to know how its properties change. And we, of course, we're going to assume, we're going to apply this to a dash ket that is a eigenket of A. A can be whatever, momentum, spin. It also, I happen to know the energy. So it's a dual ket, right? It can tell me whatever, it tells me spin and it tells me the energy, whatever the operators are. So that's cool. And what I can tell you is real quick is it looks like I've run out of time. So what I can tell you is that what we're going to do is we're going to evolve, of course, the ket and rod next time. And then we're going to see how our expectation value changes. But you know what? You know what's actually better? You know what's better is actually to do this. Look at how this thing's property changes projected onto itself. Given that you started here, how, it's like, okay, so I told you I was running, right? So I lost 20 pounds. I can either tell you that, you can track that difference, or you can take a picture of me 9 months ago. I haven't aged that much, but I am 20 pounds thinner. Right, so this is like, okay, I was 190, what's the difference, how did I fit into my old self? So anyway, so that's the thing you can do. What you're gonna find is that, get this, when you're working on eigenstates of a Hamiltonian, we'll do this next time. When you're working on eigenstates of a Hamiltonian, there's no time to do this. So, whatever spin is, average z spin, over time, the average doesn't change. There's no dynamics. And this is the answer to one of your homework questions, by the way. You're going to actually do the calculation I meant to do now, but I ran out of time. So when you are evolving a state that's an eigenstate of the Hamiltonian, anything you can measure doesn't change. So time-dependent quantum mechanics is useless. Take your state, it's an eigenstate, make your measurement, and forget about it, you're done. It never changes. I'm going to show you that next time. Now this brings up kind of a really big deal. Why does anything change? Why am I moving right now? Right? I can't move if I'm stationary. If my expectation values never change, if I never consume ATP, if I never move, then the universe is in a perfectly zero entropy crystalline state, and nothing ever moves. So I just showed you that eigenstates of the Hamiltonian don't move. There's no dynamics at all. So again, next time we're going to talk about why does the universe evolve in time? Why am I talking? Why is the sun burning? That's because nothing is ever